Today's lesson we'll be doing section 10.6, which is about exponential growth and decay. Okay, we'll be using exponential growth and decay models to predict future events. Okay, we will be using the base E. Okay. And we'll start with exponential decay. There's two formulas for exponential decay. One deals more in a financial sense, one deals more in a scientific sense. This is a more financial sense. Okay, when a quantity decreases by a fixed percent each year or a period of time, the amount or y of that quantity after t years is given by this function where the amount after the time equals the initial amount minus 1 or times 1 minus the rate raised to the time period exponent. R is called the rate of decay in this case, and when we're decaying, it's always subtraction on our formula. Car depreciation example of exponential decay, and we have an example right here. It says, this is an example of decay of a computer's value. This Industries bought a computer for $2,500. It is expected to depreciate at a rate of 20% a year. What would be the value of the computer in 2 years? Okay, so some of the important information is the initial value A is 2,500. The rate of decay is 20%, and the time is 2 years. Remember, when we use a percentage, we never use it as a percentage, use it as a decimal. Okay, so in our formula, okay, our y value or our amount after 2 years is equal to 2,500 times 1 minus 0.2 raised to the second power. Okay, your calculator again can help you a lot with this scenario, okay, or in this case it's really 0.8 to the second power. Okay, combine it all together, it tells you that your computer would be a value of $1,600 after 2 years. And this is exponential decay in a more scientific method. Okay, it's using the E number, okay, or the natural base. Okay, another model for exponential decay is preferred by scientists to solve problems involving radioactive decay. Okay, it's y equals the initial amount times e to the negative k times t power, where a is the initial amount, t is the time in years, and k is called the constant of decay. Okay, so here's our example. So sodium half-life of sodium-22 is 2.6 years. What is the value of K for sodium-22? K is the constant of decay. Okay, so when we're describing a half-life, okay, we have an initial amount of A. We want to know, okay, what this K value is. So we want to know what the K value is when we have half of the initial amount left over. So half of A or 0.5 of A, and we have 2.6 years. Okay, so now we're solving this for K, which means we need to isolate the E, use a natural log, okay, and solve for K. And we get the rate of decay at 0.2666. We also have exponential growth. The exponential growth model is going to look very similar to the decay model, except for growth, we're going to use addition. We're adding. Okay, we still have an initial amount A. We still have the percent of increase, which is R. Okay, we still have the time period, which is T. R is the rate of growth, okay, and Y will be our amount that we have grown after this time period. Again, this expression is used more in a financial sense, okay, how something can increase in value, or a population. Okay, population of a city of 1 million is increasing at a rate of 3% a year. If the population continues to grow at this rate, in how many years will the population have doubled? Okay, so we're looking for an initial amount. We have an initial amount of 1 million. We're looking for when the final amount is double, which is 2 million, and we have a rate of growth of 3%. So we set up our equation to find our t value. Okay, so we have 2 million equals the 1 million times 1 plus 0.03 to the t power. So it's looking like that. Where did the 2 come from? And what happened is I divided both sides by 1 million. And you divide both sides by 1 million, and you get the 2. Now we can use a common log on both sides in order to solve. And we have 5 years. We also have an exponential growth model that again is used by scientists. K again is a constant of growth that we call it. A is the initial amount. Okay, we use our base E, and T is in is our time period again. Okay, so here's our last example. And it says, as of 2000, Nigeria had an estimated population of 127 million people, and the United States had an estimated population of 278 million people. Populations of Nigeria and the United States are modeled by these functions. This is Nigeria, okay, and this is the United States. Okay, they have different constants of growth. Okay, according to these models, when will Nigeria's population be more than the United States? This example I'm leaving for you as evidence of watching your video. Okay, so you have one example to bring in tomorrow for credit, and we will go through this tomorrow.